This talk first briefly describes the classic single-wire telephone and how it works. It then covers the reasons why I decided to try to improve the design for serious expedition use. The resulting phone is described along with the results on an actual expedition. This work builds on the single-wire data link that I presented at last year's C&E session for transferring survey data. It was Bill Stone who coined the name Ultraphone. For local use in cities, the first telephones used iron wires strung on poles with an earth-ground return path, exactly the same as used by the telegraph during the Civil War. The phones used high-output carbon granule microphones and sensitive high-impedance earpieces. Because of interference, these had to be phased out once AC power started to be common in cities. The single-wire concept is still useful in rural and mountainous areas around the world where many large caves are located. The first single-wire telephone for cavers was designed in Australia by Michie. For reception, it used a single 741 op-amp configured as a unity gain, non-inverting follower with a high input impedance, which fed a high impedance telecom earpiece. For transmission, it used the telecom earpiece as a microphone in an inverting amplifier circuit with gain. A 9-volt battery allowed up to about 7 volts peak-to-peak voice transmission on the line. Because the receive circuit had unity gain, it could always handle the incoming signal without overload. This is a good design for short lines and in fact can sometimes be used with just the operator's body as a ground. Several years ago, Bill Stone asked me about the possible use of through-the-earth voice radios on his expeditions to Sistema Chevy in Mexico. Based on depths and distances, power requirements, and complexity, I said, no way, and recommended single-wire telephones instead. Bill then contacted David Larson, who had experience with single-wire phones. David built phones for Bill's 2017 expedition. His phones had unity gain reception, but changed to rechargeable Stenlite lithium batteries, which are 8-volt maximum, giving about 6-volt peak-to-peak audio output onto the line. He did add a call buzzer or ringer. Because the telecom earpieces were no longer available, he was forced to change to an 8-ohm loudspeaker with a matching transformer. When listening, this reduced the audio output to less than 20 milliwatts, which required holding the phone close to one's ear. I asked Bill about the length and condition of the phone line and grounds and about problems with noise, voice strength, etc. I first suggested replacing the existing grounds with thin stainless steel sheet buried in mud or placed in water, even if the good ground was some distance from the camp. I also suggested loosening and retightening every accessible wire nut to ensure good connections. I decided to use the model of the single wire line that I developed for the data transfer project to estimate voice loss in a less than perfect line. I modeled a long phone line with poor grounds and various series and shunt defects. I concluded that what was needed was a phone with adjustable receive gain and strong receive audio, along with much greater and adjustable transmit voltage. Bill sent me David's phones, but I could see no way to add these features to them. These are the features I wanted and I got in my new design. The LM386 seemed like a good integrated circuit to start with because it will work on 7 to 9 volts, will drive an 8-ohm loudspeaker directly, and has a very low DC idle current. The LM386 has been around since 1969, when tubes were still common. It is only stable for gains greater than 5, which gives it gain into the megahertz region. For a 1 watt amplifier, it has remarkably low idle current of only 5 milliamps. It has a built-in fixed gain of 20 or 26 dB, which I use for both receive and transmit in this design. The receive input impedance is 100,000 ohms at low volume, decreasing to about 39,000 ohms at 1 kilohertz frequency at maximum volume. D3 and D4 diodes protect the LM386 input, while R4 limits the input current and reduces loading of the line. C4 and C6 limit the amplifier inputs to audio frequencies to reduce RF pickup. C8 and R6 are necessary to prevent high-frequency oscillation because the LM386 has gain beyond 1 megahertz. C5 reduces low-frequency power line hum pickup. In transmit, the push-to-talk switch S1 activates the relay RL1, which switches in the microphone and transformer T1, stepping up the output to as much as 40 volts peak to peak on the line. The microphone M1 has about 10 dB greater output than typical electret microphones, further boosted by R2, which is 10,000 ohms instead of the usual 2.2 kiloohms. The complete circuit adds the clear LED D1 as a very low current power on indicator and a second red LED D6 that flickers as the operator talks to guarantee that transmission is actually happening. The value of C6 is increased to improve RF filtering. A call function is included. Holding the phone upside down activates tilt switch S2 that exchanges the microphone for piezo buzzer B1. Pressing the push-to-talk puts a loud, annoying tone on the line. This call feature was borrowed from David Larson. The simple classic single-wire telephone with built-in battery may be best for cave rescue situations due to its very long battery life and lack of gain adjustments, which do require a little training. The Ultraphone excels on very long party lines with multiple users and poor grounds, and at cave camps where everyone can hear both sides of the conversation. The Ultraphone's transmit level can be turned down to make it compatible with the original classic phones. This phone is identical to the ones used on Bill Stone's 2021 Chevy Expedition. The Expedition version of the Ultraphone is designed to hang on a wall at a cave camp and be left connected to the line and ground. The external battery is plugged in only for scheduled check-ins or emergencies. As you can see, the feedback from Bill was pretty favorable. It took him 5 days of hard caving to return to the surface from the far end of the phone line, when it would take just a minute to pass a message over the same route. For those who missed the talk last year, the data sharing was done with the same Samsung Note Active tablets that were used with TopoDroid and Disto X2s for surveying and sketching of the cave. I built passive interfaces to connect the tablet's audio output, input and output to the line, and used an existing Android software modem application to convert data to audio tones and back to data. This is the prototype of a self-contained phone intended for all-round use. It is identical to the Expedition phone except for the internal 9-volt battery and the addition of a reverse polarity protection diode. Note the different position of the microphone. The battery is a very tight fit in this case. The stiff on-off push button is unlikely to switch on in a cave pack. For years, I've been trying to devise a simple way to use a single wire line for voice communication while on the move without having to strip off the insulation to make a direct connection to the wire, which would damage it. The traditional method uses RF at a half a megahertz to 2 megahertz with FM or single sideband modulation with small loop antennas, which allows two mobile units to talk to each other or to the surface. The antennas can be held up to a couple meters from the wire. This requires complex and expensive gear and also has a short battery life. In the past, I've tried coupling audio frequencies onto the phone lines directly using clamp-on ferrites, ferrite rods, and slotted metal toroids, but none came close to working. I decided to simulate capacitive coupling near the middle of a 3-kilometer line with poor grounds and ultraphones connected to each end. The mobile phone used only 18 picofarads of coupling and a poor ground. All three phones had their gain set to maximum. The fixed phones at each end received 26 millivolts peak to peak from the mobile phone, which in turn received 140 millivolts peak to peak from the fixed phones. These were not high levels, but were enough for two-way voice. I then realized that the capacitance of the human body to ground is 100 to 200 picofarads, no matter how close to ground they are, which is much larger than the 18 picofarad line coupler. This means that the mobile phone does not benefit from a ground connection and can simply be held in a bare hand. I assembled the test setup shown here with the 33,000 picofarad capacitor simulating the loading of 3 kilometers of wire. I had no trouble communicating with the mobile phone with good sounding audio both ways. The weak point of the link is the transmit audio from the mobile phone. I realized that because the mobile ultraphone is operating into an open circuit, I could utilize the full output winding of the existing step-up transformer to nearly double the phone's output to close to 80 volts peak to peak, which boosted the output by 6 dB. I then built the simplified dedicated mobile phone shown here, which includes the 6 dB transmit boost. The mobile phone has no gain controls, but the built-in battery requires an on-off switch. The built-in test equipment for power on and voice transmit is retained. Email me with any questions or comments. The Ultraphone circuit boards are set up to be universal. They can be configured to use an internal 9-volt or external 8-volt or 12-volt battery. They can also be used to make a dedicated mobile phone.